Hello everyone and welcome to this module on Introduction to Continuum Mechanics. In this module, we're going to discuss the principal stress and maximum shear stress. And by principal stress, I mean maximum and minimum normal stresses. So I'd like to start this part with a motivation. From your strength of materials or mechanical materials course, you basically remember the Mohr circle. This is the schematic of a Mohr circle where we had normal stresses on the x-axis and shear stresses on the y-axis. And basically, if you remember, this is a 2D Mohr circle. So we had a minimum value for sigma and a maximum value for sigma. The normal stresses. And here we had the maximum shear stress, tau max. And if you recall, here when we have the maximum and minimum normal stresses, tau, the shear stress, is equal to 0. However, if we find the corresponding normal stress for the maximum shear stress, it is not equal to 0. And today we're going to basically learn about these things and basically derive the equation for the maximum shear stress, as well as finding sigma mean and sigma max, and also corresponding this normal stress for the maximum shear stress by solving an equation which is basically based on continuum mechanics, because Mohr circle actually was discovered way after these kind of equations were developed. All right, so let's get started by the principle of stresses. So you basically know that we had this T as stress tensor, T11, T12, 13, T21, T22, T23, T31, T32, and T33. So we all know that this T, we already proved this and mentioned that T is basically a real symmetric stress tensor. So T is real symmetric, is a real symmetric tensor. Therefore, we expect, let me just put it down in here. Therefore, we expect to get real values for eigen value, and also we have mutually perpendicular eigendirections. We may call them principal values in principal directions. So therefore, for example, we will have E1, E2, and E3 as the principal directions here, or generally N1, N2, and N3. And here we can have T1, T2, and T3 as the eigenvalues. And these principal directions basically are the normals to the plane. So by knowing the normals to the plane, we will be able to know that on which plane the maximum or the minimum normal stress basically act. So if this is N1, we know that this is the plane that it acts on. And how we can get these eigenvalues and eigenvectors. So we already discussed this in the first module. You can use the eigenvalue and eigen vector analysis, and basically you solve the characteristic equation, and you take out these three values from here, t1, t2, and t3, and you finally write t as t1, t2, and then t3. So the shear stresses are totally zero. This is the same as we had in the motivation part, that shear stresses are zero. We only have the normal stresses. So basically this means that when we have the maximum and minimum normal stress, shear stress is zero. So this is quite straightforward. However, for the maximum shear stress, this is not that straightforward. So why shear stresses are important? So if we have, for example, a bar like the one you see in here, and it undergoes tensile stress in here, so you have stresses in here. So in a plane which basically creates an angle of 45 here, we will have the maximum shear stresses. And you know that this theta 45 here corresponds to 2 theta, or half pi in here on the Mohr circle, where we have the maximum shear stress. And this is basically, let's say, is responsible for the failure of the ductile material under under normal stress. So you will see these oblique kind of surfaces on these materials. So that's why it is important to identify these maximum shear stresses as well. So in order to find the maximum shear stresses, we basically have T1, T2, and T3, and we know the eigen directions. So let us assume that T1, T2, and T3 are principal values, or our eigenvalues. These are the same, terminology. So maybe I change this to principal values, and these are principal directions. And also E1, E2, and E3 are principal directions. So now we would like to find the plane or the directions where the maximum shear stress basically acts on. So we want to find this N. So then we have an arbitrary normal, or N. which is N1 E1 plus N2 E2 plus N3 E3, where the maximum shear stress stresses act on. All right, so from the previous module, you know that if we have an arbitrary plane in here, so and we have a traction like this is T, then we have a normal for this surface N, and we basically can find the normal stresses and shear stresses from here. So I use tau S for the shear stress and sigma N for basically the normal stresses. The book actually used Tn instead of sigma N and Ts instead of tau S. So T is basically, let's say T1, T2, and T3. So we have T1, T2, and T3, which are the eigenvalues or the principal values from our, maximum principal stress, times N1, N2, and N3, which is our unknown in here in this problem. So based on this, we know that T is sigma N plus tau S. So traction is equal to sigma N plus tau S. And here, tau S becomes T minus sigma N. So if you want to find the magnitude of tau S, we basically put it into two pipes, or the absolute value is T squared minus sigma N squared. These are two vectors, right? So we have to find first T. So T here is T1 N1 E1 plus T2 E2, N2 E2 plus T3 N3 E3. So this is T. And now we have to find sigma N. We know that also sigma N is T dot N. So if we have this theta again here, so we know that T dot sigma N is basically the projection of T on sigma N. So if we have the cosine theta, it is basically sigma N divided by T. So here, instead of sigma N, instead of T, we have sigma N. So we have T sine theta and then cosine theta. So basically we are calculating the projection of T on this red vector sigma N. All right. So if we have, so then we have sigma N is equal to T dot N, where this T is T1 N1 E1 plus T2 N2 E2 plus T3, N3, E3 dot. Here we have N1, E1 from here, plus N2, E2 plus N3, E3. So we get T1 N1 squared plus T2 N2 squared plus T3 N3 squared. And now to find this value, then we get tau s squared, or let me write it down in here. So tau s squared is equal to, so t squared, so each element, sorry, it is here. So each element should be squared. So let me just draw a line around this, as well as this one. So this is sigma n. So it becomes T1 squared N1 squared plus T2 squared N2 squared plus T3 squared N3 squared minus this whole squared. So T1 N1 squared plus T2 N2 squared plus T3 N3 squared. This is also important because this is the equation that we are going to deal with throughout the rest of the video. So we have to find the maximum and minimum of the shear stress, is this tau s, using this equation. So basically, if you look at these squared powers in here, so you see that by equating n1 equal to 1, n2 0, and this 0, then you get t1 squared minus t1 whole squared, t1 squared, so this becomes 0. So if you take, for example, n1, n2, and n3 in here, and if you use 0, 1, then the rest 0, you get tau s equal to 0. And since these are, even powers, so also minus 1 works. So again, if you put n1, n2, and n3 equal to 0 plus minus 1 and 0, you get tau s equal to 0. And n1, n2, and n3 equal to 0, 0 plus minus 1, again gives tau is equal to 0. So all of these, they get tau is equal to 0. And here we show that this tau is equal to 0 is the minimum value for the shear stress. This is the minimum shear stress. And why this is the minimum shear stresses? So basically, since we have here T1 as a real value, so if you have a real value, either positive or negative, when you power it to an even value, to an even number, you get something positive. So everything is here is somehow positive. So tau s squared is positive because these are all real numbers. So what we have here is also a real number. So then the maximum of tau s, then the minimum of tau s squared is definitely 0, and its maximum tau s squared should be something positive. So that's why we say that tau s squared is equal to 0 is the maximum shear stress, and therefore tau s equal to 0 is the minimum shear stress in here. So let's write this in here. Since we have n1 squared, n2 squared, n3 squared, and also t1, t2, and t3 are real values, therefore we get a positive answer and also a negative answer. Yeah, negative answer that both hold true. So we can say that the minimum shear stress is 0. So now that we have found the minimum shear stress and also its principal directions in here, we have to find the maximum shear stress. And one thing that you have to notice is that these plus minus 1, they basically are indicating one plane. So if you have a plane like this, so one n is in this direction and another one is in this direction. So it is basically just one plane. So in order to find the maximum of this expression in here, let me just copy and paste this. So So in order to find the maximum shear stress, you remember from your undergraduate and also from high school that if you have a function like fx and you want its maximum or minimum, then you use the derivative. So we calculated f prime of x and we equated equal to 0 and we found those x basically. We are using the same terminology in the same concept in here to find the maximum values. However, here we also have to make sure that these n1, n2, and n3, since they are unit vectors, they also should satisfy another kind of equation. So since n1, n2, and n3 are unit vectors, so n1 squared plus n2 squared plus n3 squared is equal to 1. So in mathematics, we call this a condition. So basically, this whole problem here is an optimization problem. So in optimization problem, we're going to find the maximum or the minimum of a function. And here we have a condition here. So it is subjected to, so this stands here for subjected to a condition which is showed by g of x. And here g of x is this equation here, where we basically write it like this in optimization, and f of x is basically this equation in here. So let's get started. So here t1, t2, and t3, they're like real values, and n1, n2, and n3 are unknown. So we can write tau s squared as a function of n1, n2, and n3. And the book actually use tau s squared. It's because it's much easier to work with tau s squared than tau s, because then you have to put a squared root in here and everything gets really complicated. So if you want to calculate the derivative of tau s squared, since this is a multivariable function, so we have to use the partial derivative. So we have the partial derivative of tau s squared with respect to n1, sorry, partial n1 dn1. And this is basically the same as y, for example, equal to, or f of x1, and x2, for example, is equal to, for example, x1 squared, x2 cubed. Then the partial derivative of, df is equal to the partial derivative of f with respect to x1 dx1 plus partial derivative of f with respect to x2 dx2. And here we can simply write, in the first expression, we assume that this is a constant value. So we write 2x1 dx1 x2 cubed plus, then we assume that this is, let's say, a constant value, so x1 is squared. Then we have 3x2 squared dx2. So these are basically these in here. Plus partial derivative of tau s squared with respect to n2 dn2 plus partial derivative of tau s, tau s squared with respect to n3 dn3. And in order to find n1, n2, and n3, so we equate this equal to 0. So when this equation becomes zero, it is when we have this equal to 0, this is equal to 0, and this is equal to 0, which is our trivial solution. But we are not looking for the trivial solution. So looking at the non-trivial solution, we can see that these here, and also from here, we know that n1, n2, and n3, they're not independent. So they are dependent. So if I have my n1, let me write it with another color, n1 squared plus n2 squared plus n3 squared minus 1 is equal to 0. So if I take the derivative of this expression here, so I get 2n1 dn1 plus 2n2 dn2 plus 2n3 dn3 is equal to 0. So by comparing, let's say this is 2 and this is 1. So if you compare and if we get rid of these 2's in here, so you see that partial derivative of tau s squared with respect to n1 is equal to a multiplier, like I can put any number here, then times n1. So comparing 1 and 2, we get partial derivative of tau s squared with respect to n1 is equal to this n1 and a multiplier like lambda. Then we have this partial derivative of tau s squared with respect to n2, which is equal to a multiplier then n2. And then we have the partial derivative of tau s squared with respect to n3, which is equal to lambda n3. And I used lambda here because I can get rid of it simply because they are all lambda. So I can just remove all of them. So this lambda here is called the Lagrange multiplier. So where lambda is known as Lagrange multiplier. So basically we are solving this optimization problem using the Lagrange multiplier. We are breaking this equation into some other equations which we can solve linearly. Here we had n1, n2, and n3 as unknowns, and here we also introduce a Lagrange multiplier like lambda, which is also unknown. So here we are increasing the number of unknowns by 1, and basically then we solve for n1, n2, and n3 as well as lambda. And this value of lambda does not affect our finite solution, and this is the beauty of Lagrange multiplier approach. So now I have these expressions in here. So I have 3, so 3 1 3 2 3 3 I call them, and then I also have this equation here. So if I just copy and paste this in here, so then I have 4 equations, 1 2 3 and then 4 equations. So equations 3 and 4 form 4 equations from which we can solve, or we can find n1, n2, n3, and lambda. So equation 3.1, which is the partial derivative of tau s squared with respect to n1, and tau s is this here. So if I copy, paste this in here, So this is equal to lambda n1. So if I take the derivative, so this expression here becomes 2n1 tn1 squared. Then this becomes 0. This is 0 minus. Then I have 2 in here. So I put 2 in here and I rewrite everything in here. T1 and 1 is squared plus n t2 and 2 squared plus t3 and 3 squared times. Here I have 2 and 1 t1, then these are 0. This is equal to lambda n1. So if I put this 2 in here, so if I multiply this 2 with this 2, it gets 4 in here, and this is the final equation here. So if I repeat this, here, and then here, so I will have 3.2. It is a partial derivative of tau s squared with respect to n2. And this is, of course, n2. So what I get is n2 t2 for this expression, and n2, this is t2. This is 2. And this is 3.3. So this is n3. And here we have n3 lambda n3 t3 4, and this is n3. This is t3, and this is n3. So now we have 3 equations in here, and then we also have the 4th equation in here. So then if we solve, so solving 3.1 to 3.3 and equation 4 simultaneously, then we will be able to get 12 answers. And with 6 answers, so from here, from star, I call this, we get 18 overall answers for the combination of n1, n2, and n3. But since I already mentioned that some of them, like, plus minus 1 0 0, so this gives one value, and here also this is repeating in here in equation 3.1 to 3.3 and 4, then they also refer to the same plane. So we get 18 overall answers by removing repeated directions or answers. Let's call this answers. We get 9 directions or principle here, directions where the shear stress is either maximum or minimum. So these planes, these directions are given in table 4.1 of the book. And if you notice in this table, the values for tau s squared are given. And if you want to get the maximum of tau s, so we have basically T1, T2 in the pipes. So these are absolute values, and then we have the difference between T1 and T3 divided by 2, and then we have T2 minus T3 divided by 2. And basically tau s is the maximum of these values. So basically, if we can find the maximum of T1, T2, and T3, as well as its minimum, we will be able to find tau s max. So if we have T1, T2, T3, we don't know which one is, but we know that we have the maximum minus Ti minimum divided by 2. This will give us the maximum shear stress. So if we have, for example, T1, then T2, and then T3, this is going to be T1 minus T3 divided by 2. Or if this doesn't make sense. So if we have, for example, T2 larger than T1 larger than T3, then we have T2 minus T3 divided by 2 as the maximum shear stress. And here, the corresponding normal stress is, of course, as I already mentioned here in the Mohr circle. So here, this radius is basically sigma max plus sigma min divided by 2. So here we have Ti max plus Ti min divided by 2. So if you have, for example, let's show this on the Mohr circle. So if you have T1 equal to T2 equal to T3, then we get tau s as 0. So then the Mohr circle becomes a point where we have the hydrostatic stress state. And shear stress is basically on all planes is equal to 0. So in the hydrostatic, the shear stresses are 0. And also, if you have, for example, T1 equal to T2, which is not equal to T3, so you have two principal stresses equal to each other, then this corresponds to E1 and E2, let's say, or N1 and N2, then you will have infinite number of solutions that you can get by rotating E1 and E2. So if you have a plane where its normal is E3, so you have infinite numbers of solution that you can rotate, that you can find by rotating these E1 and E2 around this E3. But basically it doesn't affect your maximum shear stress. This is also true for, when you have T2 equal to T3. So you have E2 and E3. So this becomes E2 and this is E3 and this is E1 basically. So I will also solve the equation regarding this optimization problem in Maple, so you get the whole idea of this optimization problem in here. So I'm going to draw a box around it. So you can also see the solutions, and there's also an appendix at the end of this chapter. You can go and read it in detail, and it mentions in detail how you can derive all these, these directions N1, N2, and N3. Well, I thought that it might be a good idea to also explain something about the first paragraph on page 166, or the last paragraph of the topic section 4.6. So basically, this paragraph talks about different values and different scenarios for T1, T2, and T3. So first we had T1 not equal to T2 not equal to T3, and these eigenvalues, they each had eigendirection. This was totally clear, and we actually solved for that. But also the book mentioned another case where we have T1 equal to T2 not equal to T3, and it says that we have infinite number of planes in E1 and E2 direction where they form a plane, and we have N3, which is the corresponding eigenvector for T3, which is normal to both E1 and E2. So I wanted to mention this, and I bring your attention to our discussion on module 1.2.6, where I already mentioned three cases, case 1, case 2, and case 3, where we had different values for where we have different scenarios for the eigenvalues. So here we have lambda 1, lambda 2, and lambda 3, where each corresponds to T1, T2, and then T3. So as we already mentioned, this is the case we already discussed. So we have like three different eigenvalues and three different eigenvectors. And here we have basically T1 equal to T2 not equal to T3, which is this case in here. So I already mentioned and proved that this corresponds to, alpha N1 plus beta N2. So it's like alpha E1 plus beta E2 in here. For example, these two can create any kind of, right hand, for example, a right hand basis like E1 and E2. So suppose that this is alpha 1 E1, and this one is perpendicular to this one, so this is beta 1 E2, where these form a plane P, where N3 is normal to both P and also these eigenvectors alpha 1 E1 and beta 1 E2. And also we can have another one, alpha 2 E1, which is this one, and this one is perpendicular to beta 2 E2 basically. And these two can also form a plane, and there we have N3 normal to P, both P and alpha 2 E1 and beta 2 E2. And we can also go for infinite number of planes which are formed by these two, alpha E1 plus beta E2. So that's why we have infinite number of planes. And then we have the case where T1 is equal to T2 is equal to T3, and so any vector becomes a principal vector. And here you can see that T1 is equal to T2 is equal to T3. So tau s, or the maximum shear stress, it becomes maximum of 0, 0, and 0. So it basically vanishes. And also, in let's say in example, so in example 4.6.3, we have a problem where we have T1 is equal to, T1 is equal to T2 not equal to T3. And this basically corresponds to this case in here, where we have infinite numbers of, alpha E1 plus beta E2 eigenvectors. They form a plane like P, where we have entry normal to them. So we have here 100 equal to 100, not equal to 500. So basically, here we have, we can form three planes. So one is with E1, if this is E1 and this is E2, and this is, for example, entry or E3, whatever. So we have one between E1 and entry. So I can write 1 as, so between 1 and 3, so it's like E1 and then N3. So for this one, we have E1 plus minus N3 divided by 2. And here, you can use E3. It's better because we want to mention everything in unit vector, because we need to say that, okay, E3 squared plus E2 E3 squared is equal to 1. And here we put plus minus because we already mentioned that if you have a plane like this one, so this is positive, and it could have a negative direction as well. So that's why we include both positive and negative. And then we can have 1 between E2 and E3. So E2 and E3, so it is E1, no, sorry, it is E2 plus minus E3 divided by square root of 2, where E1 plus E3 is equal, E2 plus E3 is equal to 1. And also we have this combination here of E1 and E2 here. So we have, let's say, E1, or let's say alpha E1 plus beta E2 plus 1 divided by square root of 2 E3, where we also know that alpha squared plus beta squared plus 1 divided by 2, so it's square root squared, so it becomes 1 divided by 2 should be equal to 1. So that's why we have infinite number of planes. So it was somehow a bit vague in the book, so I wanted to mention this.
Right, so here in the first line, I basically call the relevant package here, which basically include the Lagrange multipliers in here. Next, I have my tau s squared in here. This is my basically the maximization function in here. And then I have my condition, which I used G, which is quite common notation in optimization problems. And I moved 1 to the left side of this expression in here. So then we have the Lagrange multipliers, where we have to pass our function, and then we put the condition, because we might have more than one condition, so we put it into these brackets, and then we have n1, n2, and n3, because in Lagrange multiplier we do not want to, because lambda is not important, so it does not affect our solution. So then I assumed that T1, T2, and T3, their absolute values is positive here, because I wanted to assert that these values are real. So I use these assumptions in here. So then I get 19 answer for the principal directions. So these are, the first 6 answers that I already wrote down. So we have 0, 0, plus minus 1, 0, plus minus 1, and then 0, plus minus 1, and then 0, 0. And then we have 12 other answers from the second part of the problem, where we had the Lagrange multiplier lambda included into the problem. And then here I evaluate, in a for loop, I evaluate tau s squared for, different values in here that I get, because then I'm going to print them in a loop in here. So in this for loop, again, I print the answers. So I have my principal directions as well as, its corresponding value. So here you can see that the first 6, which corresponds to the first 3 principal directions, I get tau s equal to 0. And then I have, this is tau s squared basically, because it is this value. Then I have, 12 other answers in here, which are, the same 2 by 2. So if I have this and this, they correspond to the same principal direction, because they only differ in a minus sign. So I have 3 from here. This is 4, and this is going to be 5, because they only differ in a minus sign. And then I have again this one and this 6, and this is 7 answer, this is 8, and this is the 9th answer. And if you, for example, look at this one, it is t1 minus t2 squared divided by 2, and basically this corresponds to 9 answers that you already saw in table 4.1.